Hello, everyone, and welcome to Royal Circuits and Advanced Assemblies Tech Teach Talk Thursdays. Every week, we've been presenting a new topic related to printed circuit board design, fabrication, and assembly. This week, we're going to be talking with Mike Konrad, owner and president of Aqueous Technologies, a printed circuit board cleaning solution company. Well, Mike, thank you so much for joining us.
Well, thanks for inviting me.
Before I tell everybody a little bit about the companies, would you like to tell us a little bit about yourself?
Sure. I've been in the electronic assembly industry since 1985. I started when I was 4 years old, and I was 35 years old. And in 1992, I founded Aqueous Technologies. I've been involved in the cleaning industry since '85, and then jumped into the deep end of the pool in 1992, when I started Aqueous Technologies. We manufacture cleaning equipment for post-reflow circuit assemblies, as well as cleanliness testing equipment, rose testers, and ultrasonic stencil cleaners. So I look at the world through cleanliness lensed eyeglasses. So I look at everything as in terms of clean or dirty. And I'm also the host of the Reliability Matters podcast, which is a podcast dedicated to the reliability of circuit assemblies. We talk about we don't talk about cleaning very much, but we do talk about best practices in X-ray and reflow and thermal management and printing and pick and place and pretty much every aspect of the assembly industry as it relates to reliability.
Wow, I've listened to your podcast. It's a great one. If you guys are looking for something to listen to as you start heading back to work, check out Reliability Matters by Mike Konrad. Today's podcast is sponsored by Royal Circuits and Advanced Assembly, the original quick-turn printed circuit board manufacturing experts. If you guys need a board faster than you knew was even possible, give us a call. We can actually turn out boards, and in a shift, we can populate boards, including sourcing parts. If they're available, we'll get them. And we can do that in under a day as well. Our turn times can be measured in hours to really whenever you need it. So with that, Mike, I'm going to get out of the way and turn it over to you. If you have questions as we go along, please ask them in the question and answer box below, and I'll pose them to Mike when the time's appropriate. Thanks, everyone. Mike, the floor is yours.
Thanks, Mark, and thanks everyone for joining us today. I know your time is valuable, and I was impressed with the number of people that logged on to this as well. So either first for cleaning knowledge or Netflix is out of shows. I'm not sure which it is, but I'm happy either way. The agenda today, get this going. We're going to talk about several things. One is modern cleanliness expectations. What are the current cleanliness expectations? We're going to talk about reliability as it relates to contamination. We're going to talk about, oh, I apologize. I have I'm working from home and we have dogs downstairs. So sorry about that. We have a contract with No Clean. Many years ago, No Clean came onto the market, and we kind of have an implied contract with No Clean. Is cleaning necessary? It may or may not be necessary for you. We're going to talk about how to quantify that answer. We're going to talk about contamination target lists. We're going to talk about electrochemical migration, otherwise known as ECM. We'll discuss contamination failure mechanisms, the requirements for ECM. If you really are hell-bent on having an ECM event on your board, I'll tell you exactly how to do it. And we'll talk about harsh environments and Internet of Things, which tend to go together. And then, as Shakespeare probably intended to say, to clean or not to clean. We'll get into that end of the pool as well. So let's just kind of put everything in perspective. Today, modern time, probably even more specifically today than in general, society values cleanliness. We wash our cars fairly regularly. We wash our hands. In the world of COVID pandemic, we wash our hands incessantly. We wash our dishes. We have services that wash our pets. We certainly value cleanliness. And when we check into hotels, we have a high expectation of cleanliness. When we use the restroom, I won't go into details here. You can use your own imagination, but we have a high level and a standard for cleanliness. When we go into restaurants, we demand cleanliness. In fact, I live in near Los Angeles, and Many other states have the same thing where we put letter grades on our restaurants. So if you're going out for a steak and you see a C, you know, you didn't intend to eat C food, you intended to eat A food. So we actually demand cleanliness in our restaurants. We require clean to the point of sterility in our operating rooms, operating theaters. Obviously, they have to be exceptionally clean. We verify clean. Every industry has some type of verification process on cleanliness. We even, in public restrooms, frequently see an inspection checklist to assure us the last time the restaurant, the washroom was clean. So we live in a society today that completely values cleanliness, except in one aspect of our lives, and that is where? What do you think? This. Circuit assemblies. There was a time when we valued cleanliness on circuit assemblies, but that disappeared several years ago, and I'll explain why. So first, let's talk about reliability. Let me kind of define reliability. Reliability is the quality of being trustworthy or of performing consistently well. Now, is reliability the same as quality? No. Reliability has sometimes been classified as how quality changes over time. The difference between quality and reliability is that quality shows how well an object performs its proper function, while reliability shows how well this object maintains its original level of quality over time through its conditions. So there's a difference between between quality and between reliability. Now let me bring reliability into perspective. Here is a BMW i3 model. It's a little electric car that BMW introduced a few years ago. And now this car left the factory, as did all the other cars that they produced. They left the factory passing every quality control criteria that they had. However, the car was not reliable. In 2018, BMW recalled the i3, thousands of i3s, for a circuit board issue that could cause sudden shutdowns. Now imagine driving at 75 or 80 miles an hour down the freeway and your car just decides to turn off, right? That could be dangerous. It could be quite problematic. Now, if we look at the press, here's the press report on it. Some BMW i3 models from the 2018 model year are being recalled for an issue that could cause sudden power loss and shutdown. And according to BMW, according to paperwork filed by BMW, the circuit board may not have undergone a sufficient cleaning process during their tier 2 supplier production. This is a real-time, it's just 2 years ago, this is a real-time example of a cleaning issue that landed in the auto industry that caused them to recall thousands of cars, which would no doubt cost millions of dollars. Now, I find a couple things interesting. The car industry, the automotive industry, has for many years resisted cleaning. They embrace no clean and don't clean it. However, they can't really get away with that with electric cars for a number of reasons, which we'll get into. So I find it interesting that BMW admits that they're supposed to be cleaning circuit boards. And the big takeaway is this, that they basically blamed it all on their tier 2 supplier. So if you're a contract assembler, they blamed it on you. So I just thought that part was interesting. So I like to, when we talk about modern issues, I like to put everything in perspective by getting some time reference. So I go back in our Wayback Machine and our time machine back to before 1989. So our industry can be divided into two sections, before 1989 and after 1989. Pretty much every circuit board was cleaned. We cleaned everything with very, very few exceptions. It was just part of the process. But in 1989, the US and 10 other countries, 11 countries in total at that moment, signed a treaty in Montreal, now called the Montreal Protocol, which banned most of the cleaning solvents that were used to clean circuit assemblies after reflow. That was primarily 1,1,1-trichloroethane, Freon TMS, and some other generic versions of those. The government of 11 countries decided that they would phase out production within a 10-year period. So by 1999, the US and 10 other countries would no longer be able to produce those chemicals that were commonly used to clean circuit assemblies. The interesting thing about that treaty is that, you know, if we look at today's world, we're in a very polarized world. Without getting political, I'll just say we're in a very polarized world. And if the U.S. decided to sponsor a treaty that just said, let's have all countries agree the sun goes down in the morning, or comes up in the morning and goes down in the afternoon or evening, we couldn't get all the UN member countries, I think there's 189 of them, to agree on that, because everyone just has their own, slice of reality. So the interesting thing about the Montreal Protocol and the ban on chlorofluorocarbons was that it's only one of two treaties in the history of the United Nations that was ratified by every UN nation country, every one of them, without exception. Only the Geneva Convention and the Montreal Protocol had 100% ratification. So it was a significant environmental treaty. And that changed forever how we built circuit assemblies, because necessity being the mother of invention, what happened when our cleaning solvents went away? Alternative solvents came out, but they weren't very good. Some people switched to all water-based flux and cleaned it with just water, but that was problematic in its own right. But the big thing that happened is no clean flux came on the market. So the flux manufacturers said, don't want to clean? All right, we'll give you a flux that doesn't have to be cleaned. So we kind of had an implicit contract. We didn't sign anything, but there was this implied contract with no clean. And the contract stated that the residues would be invisible. That was the promise, that we could use this flux and the residues would be invisible, and the invisible residues would be benign. And that was largely accurate at that time. Now let's look at what the context was at that time. When no clean flux came out at the very late 80s and early 90s, this is what most boards looked like. They were almost entirely through-hole, axial leaded components, dips, things like that. And there was a little bit of surface mount coming onto the scene back in that era. It wasn't the surface mount we see today. The pitch was way different. Conductors were quite far apart. It was basically through-hole components with the leads bent at 90 degrees, so they sat flat on the board rather than penetrated the board. And that was basically surface mount back in those days. So this is a typical circuit board when we decided that not cleaning the board would be a good idea. However, this is what boards look like today. It's a completely different set of circumstances. And when we made the contract with no clean, when we agreed on no clean, invisible, benign residues, that this is not the context in which we made that decision. So a lot has changed since then. So what happened when we stopped removing flux? This is if you're not going to take anything away except one thing, beside my barking dogs, take away this. What happened when we stopped removing flux? When we stopped removing flux, we stopped removing everything. And I'll make that a little bit more dramatic. We stopped removing everything. So is cleaning necessary? The accurate answer, and so many times in our industry, this is the best answer. And I hate when I hear this answer because it doesn't answer my question, but it is an authentic answer. And the answer to is cleaning necessary is it depends. Now I'm going to quantify how to determine the it depends part of it. So we can give you an answer that's unique to you. And we'll go down that road in just a little bit. But the actual answer at this moment is it depends. So I like to put everything on a scale. Let's have the no clean side of the scale and the clean side of the scale. If I had a product and you were my contract assembler and you asked me, do I want it cleaned? Maybe it's cheaper to not have it cleaned. Maybe you charge me a little more if it's going to be cleaned. Then if my product was a class 1 product, an IPC class 1 product, it was a commercial product, I would err on the side of, okay, I'm considering no clean. If the product was going to go into what we would consider a safe environment and not harsh environment, it's going to be inside and a climate controlled environment, then I would be inclined to go no clean. If the product had a shorter life expectancy, I would be inclined to stay with no clean. If it had a very low cost of failure, if it did fail, if it didn't cost much to replace it in terms of money or reputation, I would err on the side of no clean. If the product had a planned obsolescence, if I didn't want the product to last more than a few years, then certainly I would err on the side of no clean. And if it had a low density of component population, if the components were spread out, if it didn't have bottom terminated components, if it had a lot of through hole or a surface mount array that was not super dense or too close to the board, then all of those are kind of poster childs for a no clean process. However, if I had a class 3 product, military, medical, aerospace, et cetera. Maybe it was going to go in the military, medical, aerospace business. If it was going into a harsh environment, even if I had a class 1 product, if that class 1 product it was going to go into a harsh environment and I wanted it to last more than a year, I might consider moving over to the clean side for reasons that we'll get into in just a little bit. If my product had a high cost of failure, you know, if it was going into space and I had to go fix it, if it was going down an oil well and they had to pull it out, there are cases where the cost of repair just exceeds any reasonable amount. I would err on the side of clean. If it had a long product life expectation, I would err on the side of clean. If it had a high density component population, if components were very close together, if they were very tight to the board, if they had a really fine pitch, I would definitely at least consider cleaning as an option. So in the world of clean or no clean, cleaning is one of the processes that adds reliability. You can measure the added reliability if the contamination residues are removed off the assembly, because you completely eliminate one rather popular failure mechanism, and that's electrochemical migration. So cleaning does add reliability. Whether you need that extra reliability is not my position to answer. You know that better than I do. Some people don't need a board to be more reliable than it already is for reasons that we've already explained. So I'm going to get opinionated on 2 sets of slides here, and then everything else is based on facts. This is just my opinion, so throw it away or consider it or whatever you want to do. I would, you know, we consider the cleaning process a defluxing process. We buy a defluxing machine, we fill it with defluxing chemical, and we conduct a defluxing process. And the problem with thinking of it as a defluxing process is if someone tells you the flux is benign and inert and totally safe, one might think, well, if I don't need to remove the flux because the flux alone is fine, then I don't need to run a defluxing process. So what I would recommend is we get rid of the term defluxing and just change it mentally and put in your head it's a cleaning process, because that's a more accurate description. We're not just removing flux. Keep in mind we're removing everything, and I'll quantify what everything is in a moment. So consider it a cleaning process. Do you need to run a cleaning process? That might be different than do you need to remove the flux. So just consider it a cleaning process. And then when it comes to the flux that you're removing, if you're running a so-called no clean flux, the problem with the term no clean is people read that as don't clean. They read this as this is not designed to be cleaned, which is not accurate. No clean flux is named because no clean, because it is the only species of flux that if you decide not to clean it, that is the one you have to buy. You're not going to buy an OA, organic acid flux, water soluble. You're not going to buy an RMA, rosin flux, mildly activated. You're going to buy a no clean if you're not going to clean it. So no clean as an identifier is just the type of flux that if you choose not to clean, that's the one you have to use. It doesn't mean don't clean. So in order to avoid confusion, I would suggest not referring to no clean as no clean and just think of it as low residue, because that's what it is. The residue may be completely harmless, maybe not, but most of the time the residue just from the flux is completely harmless. It is pretty benign and very, very, very low solids. So it generally by itself doesn't cause a whole lot of trouble. It can, but it doesn't necessarily have to. So consider it low residue. And I think you'll do yourselves a favor. It'll help in the mindset of choosing whether that amount of low residue needs to be removed or not removed. So here's the contamination target list. We have contamination from board fabrication, everything from etch residues to hassle fluids and in between. Contamination comes in the form of component cross-contamination. Deflashing mold release agents are quite popularly transferred from the component reels to the component. And if you want to punk your technician and record him and put it on YouTube as a viral video, put a little silicone on the solder on the component that person is trying to solder, and watch the solder repel and watch the person come up with some choice 4-letter words as they don't understand what's going on. So that is an issue, and it does happen on a fairly regular basis from component fabrication residues. Additionally, the only part of the process where we intentionally add contamination is the assembly process. We put Flux on a board and other things. We also have what I like to call a Dorito effect. The Dorito effect is when every time after a break, one of the types of machines that we sell are cleanliness testers, roast testers. And we have customers that tell us, after 10, after 12, and after 3, we have spikes in our contamination. Well, what do you think that is? Nacho cheese. Yesterday, Mark Hughes jumped in at this part of the presentation and took great offense. He said I was blaming him for all the trouble because I guess that's one of his favorites there. But it could be Cool Ranch. Any type of food that gets on a person's hand can get on a board, and that can cause a spike in contamination. We also have, particularly today, we have issues with hand sanitizers and moisturizers and things like that that go on people's hands and eventually migrate over to a board and add to the totality of the contamination. Then we have this guy. This guy believes that he's on a mission to reuse his gloves for as long as possible, for years if possible. If any of you have gone on a tour of a contract manufacturer, an OEM's production facility, they usually give you a visitor smock, an ESD visitor smock. Never put your hands in those pockets because they're gross. They're just filled with artifacts from years of visitors wearing them. And one of the major issues that we have is these gloves, latex gloves, are permeable. They do wear out over a relatively, surprisingly short period of time. And when I say wear out, they don't have huge visible holes in them, but the oils from your skin, the sweat that occurs when you're wearing these gloves, will eventually permeate through these gloves and onto the board. And the problem with gloves, and this is really a COVID example as well, the problem with gloves is people wear gloves, they don't wash their hands with gloves on regularly. They never wash their hands as long as they're wearing gloves. And the gloves go from one contaminant source to another contaminant source to another contaminant source. And you think because you're wearing gloves, everything's cool, but you're just transferring contaminants via the outside of the glove and a little bit through the inside of the glove. So my recommendation is, almost surprising. Don't wear gloves, or at least wear gloves and pretend you're not wearing gloves. Hold boards by the corners and not by the surface. And that will go a long way in reducing human-caused contamination. Again, we stopped removing everything. When we stopped targeting the flux, we let everything else come along for a free ride. So here are some of the contamination failure mechanisms. It falls under the category of electrochemical migration, or ECM. Contamination-based failure mechanisms include, include ECM, and in addition to ECM, contamination can cause corrosion. It can cause a delamination of conformal coating. It can cause frequency distortion, particularly on high-frequency devices. And it can create cosmetic issues. And cosmetic is a big one, because cosmetic might be completely benign. But history confirms that if a customer sees something that they don't expect to see, the board is bad. They want to send it back to you. It's a reject. No one wants to stake the reputation on something that looks scary. So even if it's a friendly residue, completely harmless, if they can see it, it's bad. Residues create all of these failure mechanisms. And the one we're going to really drill down on right now is electrochemical migration, which has 3 failure mechanisms associated. The usual suspects of ECM failures are dendritic growth, which we'll get into in just a second, parasitic leakage, and conductive anodic filamentation, otherwise known as CAF. Now, we're going to say goodbye to CAF right now because we don't have time to talk about CAF, but CAF is a subterranean ECM issue. It occurs between the layers of the boards. You can't clean your way out of CAF. If you're concerned about CAF, which is a common issue, which destroys a lot of boards, we can talk about that separately. We have other webinars that are on that subject, and we can drill deep into that. So reach out to Mark or Lisa, wherever you got this information from on today's webinar, and they can get you more information on that. Let's start talking about dendritic growth. That's a very common failure mechanism, way more common today than it ever has been in the history of circuit assemblies. So whether it's dendritic growth or parasitic leakage, either one involves the process of laying conductive materials over insulating materials, resulting in a reduction or resistivity of electrical shorts. That is just like sprinkling metal filings on your board while the board is plugged in. Not cool. It leads to all sorts of issues. So electrochemical migration generally results in a short on the board because it's a metal crystal that grows between cathodes and anodes, following a conductive path. And when it reaches the other side, the drama occurs and you get this nice little gnarly short on the board, which chars the board. And then depending upon the amount of current and voltage, we may take that heat and convert it into fire. And because you all tend to build boards and put them inside stuff, that stuff catches fire. This is a typical progress of dendritic growth. So dendritic growth looks like the picture on the left, thanks to our friends at Process Sciences. This is a very poster child, stereotypical view of a dendrite. And that fern-like material that you see there is actually metal crystal. It is conductive. And as you can see here, it just shorted out those two terminals. The picture in the middle has a little bit of white haze on the top left part of the picture. That white haze is actually metal. It's a metallic white residue, which conducts electricity, and we can see that led to a short. And the picture on the right, and we're going to come back to this point in just a little bit. The picture on the right is a picture of a surface mount component with a dendrite growing between the polarities on the surface of the component under conformal coating. Just remember I said that, under conformal coating. That's going to be relevant in just a moment. So there is a much worse, well, not worse, it doesn't usually cause fires, but there is a much more troubling manifestation of electrochemical migration, and it's called parasitic leakage. And I think parasitic leakage is an insidious problem. And if I define insidious, the definition is of something unpleasant or dangerous gradually and secretly causing harm. It sounds pretty insidious, and indeed it is. Parasitic leakage is a short on the board, but not enough to, or it's actually a loss of resistivity, a rise of conductivity, not enough to create a dead short, but enough to create a leakage path, a current leakage path. So one of the typical manifestations of parasitic leakage, if a board is backed up by a battery, if its power source is a battery, it drains the battery in a relatively rapid time, way faster than the battery would drain over the course of its normal life cycle duties. So if you have a board that you can't keep the battery charged in it, chances are it's a parasitic leakage. Again, not enough to cause a short, but certainly enough to drain a battery. But keep calm. The problem is just temporary, and that's part of its insidious nature. The problem is temporary. So let's assume that you're in a situation where there is a higher degree of humidity. Let's assume you work here on an oil platform. If any are tired of working from home, consider there is a worse alternative. So let's assume you're working on this oil platform. It's a very moisture-rich, salty air kind of environment, and you have an instrument that requires calibration. The instrument turns on, everything looks fine, but it won't calibrate. It just keeps going out of calibration. So out of sheer frustration, you send it back to the manufacturer. The manufacturer is located in a climate-controlled, humidity-controlled, very stable climatic environment building, and they run a test on it. They have their test engineer run, and they get the dreaded no trouble found, right? What's the acronym for no trouble found? NTF? I suggest there's two acronyms that are appropriate in that situation, NTF and WTF. And that occurs when they can't duplicate the problem. The customer swears there's a problem, the manufacturer tests it in their lab, and there's no trouble to be found. It's a very frustrating situation. That's parasitic leakage. The source condition are from board fabrication residues and from component fabrication residues and assembly residues and human residues, as we defined more specifically a few seconds ago. If someone targets the flux, if you're running the, quote, defluxing process, then everything gets removed. So you're targeting the flux, and every other species of contamination gets to come off as well. It's a value proposition. Target the flux, everything else comes off with it. Target the assembly residues, all the flux comes off. Target the human residues, all the flux comes off. So that's why I say call it a cleaning process, because you're taking away a lot of things. Flux is just the icing on the contamination cake. So if I were doing this presentation live, as I do regularly, and I have an audience in front of me, I would ask anyone if they've ever subjected a bare board to an ionic contamination test, to a ROSE test. And several people scored 0. How many people found that their brand new board right out of the packaging was completely clean? All the hands go down simultaneously. I've never, in all these years doing this, I've never had someone go, we have 0.0 cleanliness numbers on our board. All boards come in with a small amount of contamination, and that amount of contamination arguably is not enough to cause a problem if it was left there. However, it's not left there. We build things on top of these boards. We add, in addition to the board fabrication residue, which is arguably small, we add component fabrication residue, we add human residues, we add the assembly process, we add flux residues, and it's the totality of these residues that are problematic. There are also mechanical things that raise the level of contamination that's on a board. So I have this theory. Most of you probably have children, and I have a theory of, if you have a child that and you don't reaffirm to them how much you love them, you just keep them abandoned in a corner, they grow up to be one of two things. They either grow up to be sociopaths and serial killers, or they grow up to be designers of bottom terminated components. That's their way of getting back at society. So bottom terminated components, also known as flux and trapping components, that's what I like to call them, quad flat packs, QFNs, and land grid arrays, and all the other acronyms that are assigned to those. These are extremely problematic because they have no clearance between the bottom of the package, or very little clearance between the bottom of the package and the board itself. So what happens is two things. Because gases cannot escape, they're trapped on that giant landing on the bottom of the component. Air cannot escape. So in the world of reflow, that creates voids. That's what's causing voiding, and voiding, of course, is a huge issue and a concern for a number of reasons, heat dissipation and others. And the exact same causes flux to not properly outgas. So no clean flux works by having activators that do the job that flux is required to do. And then these activators are burned out during the reflow process. At least they're supposed to be burned off during the reflow process. And any activators that are not completely burned off become encapsulated in a resin-rosin layer, kind of a poor man's conformal coating. And as long as the activators and some other ingredients are not exposed to the air and to the board, as long as they're encapsulated or burned off, then no clean has done its job. Then it doesn't really need to be cleaned, except for all the other residues that get to stay on for the ride. But that's the premise of no clean. The activators get burned off and the remaining activators get encapsulated. But bottom terminated components for outgassing, and you trap activators and other bad actors under these components, not properly encapsulated, not properly burned off, and that creates voiding, and that creates a potential for ECM based on all these activators remaining active after the reflow process. So requirements for electrochemical migration are three things. If you're going to create a cookbook for the holidays, you're going to give to grandma, and it's Johnny's favorite ECM recipes. Here's the only three ingredients you need: electrical bias, ionic residue, and moisture. That is it. If you target any one of those, you will not have an ECM event. You might have a million other problems in your day, but ECM will never be a problem. If any one, you don't have to take off all three, nor should you. Any one of these removed from the equation will absolutely prevent any ECM event from occurring. So let's start with the electrical bias. You could tell your customers not to plug in the board. I guarantee you'll never have an ECM event if you remove the E, the electrical bias, from the situation. However, that's not a very practical approach, so we'll drop that. A common approach, if I were to ask, if I were to say, well, how do we prevent moisture? Because moisture is a catalyst that causes all this to happen. How do we prevent moisture from hitting the board? A bunch of hands would go up and everyone would say conformal coating. And that is exactly not the right answer. Conformal coating doesn't protect against moisture, it protects against fluids. So if I took my iPhone and dropped it in a toilet, it would survive. However, it's not fluids, it's not a high volume of fluids that creates an ECM event. It's just moisture-rich air. So a humid day in Mississippi in the summer is way more than enough moisture to trigger an ECM event. All conformal coatings are permeable. They all allow small amounts of moisture to get through. They just prohibit large droplets from getting through, and those droplets would otherwise cause a short. So all conformal coatings from acrylics to permalines are permeable, and they will allow small amounts of moisture to get through. I said earlier, about 10 or 15 minutes ago, I said, remember this? This was that surface mount component that had a dendrite growing right across the surface of the component between conductors. That was under conformal coating. So because no moisture, no ECM, there must have been moisture. And how does moisture get under conformal coating? It permeates through. So conformal coating is wonderful for a lot of different reasons. It's not your choice for ECM prevention. So that really leaves ionic residue. And when we remove the ionic residue, we completely eliminate the opportunity for ECM to form. Now let's talk about harsh environments, because harsh environments exacerbate electrochemical migration. When I say harsh environment, this is probably an array of things that may come to mind. Arguably, all of these things are harsh environments. As a marine setting, an aviation setting, aboard in an unpressurized section of the aircraft that has huge temperature cycles throughout the day and is subjected to moisture. Space applications, downhole or oil field platform type applications, lighthouses. These are typically pretty harsh environments. But for many assemblies, this can be a harsh environment. This is certainly a harsh environment for people, I think, but certainly for assemblies, this could be a harsh environment. So it really depends upon the residue tolerance of the assembly. Now let's talk about Internet of Things. Everyone gets excited about Internet of Things. I'm not so excited about the way it's going, because it seems like we put electronics in things, not really because we need to, but just because we can. Everyone wants their stuff connected, right? And there are some really good applications for connected devices. Let's start with smart meters, electrical meters, gas meters, things like that. Those are more frequently connected devices now, so you don't have the meter reader getting chased away by your dog. That's a really good use of connected IoT type technology. And where are meters located? They're located outside your house. They're not in your living room. They're outside the house. So the electronics in here are subjected to harsh environments. Here's a LG refrigerator. Now that is not a window. That is actually a screen. And there are cameras inside the refrigerator. So you could be at your local grocery store and ponder whether or not you have orange juice. And you can take a look inside your refrigerator with your smart device and see inside your refrigerator. Now, these cameras are located inside the refrigerator. So I would suggest that that's probably a harsh environment. There are toothbrushes. Now this borders on creepy, but Sonos thinks that parents want to have electric connected toothbrushes so that they can spy on their children and make sure little Johnny and little Susie are brushing their teeth long enough and with vigor, I guess. Clearly, if it's a toothbrush setting, that's a harsh environment, a moist environment, and subject to vibration and things like that. So clearly harsh environment. Ring doorbells. Many of us have spent our time working from home on YouTube, watching porch pirates steal things recorded by Ring doorbells. A Ring doorbell is a wonderful device. It's a connected device, and it's outside. So it is subject to harsh environments. Then we have sports equipment. For reasons I don't quite understand, maybe except for one, we have connected devices as part of basketballs. We have accelerometers built into tennis rackets, maybe for coaching purposes. There's even connected footballs. This is actually a connected football. And I was wondering, why do we need electronics in connected footballs? And then it kind of dawned on me. I'll let it sink in. There we go. Then we have the automotive industry. Up to 30% on modern cars of the bill of materials are electronics. And in the next 5 to 12 years, from what I read, that can go as high as 50% or more of the bill of materials being electronics. And look at the electronics that are in cars. Remember, electronics in cars used to be infotainment. They were not really safety. They were just infotainment. They were gadgets. Now we have engine electronics, transmission, chassis, passive safety electronics, driver assistance electronics, passenger comfort electronics, entertainment systems, there you go, and integrated cockpits. I mean, it looks like an F-18 inside a lot of these cars, but unlike F-18s that have, and commercial aviation that have 2 or 3 redundant computer systems as backups, cars don't. Cars have one computer that tends to run pretty much everything. Then we look at electric cars. Electric cars, the new low voltage is 48 volts. The new high voltage is 1,000 volts. And now I'm reading 1,250 to 1,400 volts. You have to have a very clean board, folks, if you're going to run more than 1,000 volts through it. You can't even have non-ionic debris on the board, because that could definitely lead to all sorts of problems, including fires. Let's talk about how in the auto industry, we've gone from using electronics as entertainment to depending on it to save our lives and to keep us safe. This is the Tesla car in autopilot mode, where probably one of the worst names for a technology in a car, because I think it gives people a very false sense of security. But anyway, this person is driving completely on their own. And that is could be problematic if the electronics fail, particularly without warning. This is the board, one of the boards that is used in the autopilot scenario. This is, I don't know how many layers this board, I know it's multi-layer, I don't know how many layers this board is, but look at the density. Look at all the bottom terminated components. Look at the packaging on the board. It is a very, very highly dense, low profile circuit board and circuit assembly. And where do we take boards that are in cars? We take them into harsh environments. We take them into harsh environments regularly. Slow sleet, hail, sun, rain, etc. These boards are subjected to harsh environments. I have other images, which I don't have on this presentation, that show on the motors, in the motors themselves, the actual cavity of the motor assembly, there are circuit boards in the Tesla motors. So clearly harsh environments. I have 2 cars. I have my weekend car, which is a 1968 bright red Mustang, and I have a late model GM product. And on my 1968 Mustang, if 100% of the electronics fail, not electrical systems, if 100% of the electronics fail, what would stop working? Drum roll. That, my AM radio, which I don't use anyway because it's really crappy. But that's the only thing that would fail. That's the only electronics in the car. Everything else is electrical. My points, my condenser, even the capacitor that runs the blinker. It's just electrical, really. It's not a circuit assembly. The only circuit assembly in that entire 50-plus-year-old car is this right here. On my other car, my late model GM product, it has a host of technology in it. It has adaptive cruise control, which will slow me down if I'm approaching cars and keep a distance. It has blind spot monitoring. It has collision detection, automatic braking. It even has lane centering. It will, if I'm drifting out of a lane without my turn indicator on, it will actually turn my wheel automatically, kind of nudge it out of my hand and bring me back to the center of the lane, which are all pretty cool technologies. Now, all these technologies have made me a worse driver. And I love cars. I'm a bit of a motorhead. I love driving. And I usually, when I first got this particular car with all these safety features in it, I didn't trust my adaptive cruise control. I had my foot over the brake as I was approaching cars. I didn't trust the blind spot monitoring. I always looked over my shoulder. Now I trust those technologies. I don't generally look over my shoulder. I don't put my foot over the brake as I'm approaching cars. I don't worry about backing into something. I look at the camera or I listen to the audio and all that. So I've become kind of a worse driver because I'm relying on the technologies. Well, if those technologies fail, it could have devastating results. It could kill me. So the expectations of reliable electronics in the automotive industry has gone from the ability to listen to your favorite comedian on XM radio to not getting into an accident. So reliability expectations on cars are way, way higher relative to the electronics in the cars than they used to be, than they've ever been. So today, we are building boards with higher densities, many times higher voltages, and voltage is a key to ECM. The higher the voltage, the greater the ECM potential. It can happen on low voltages, but it just gets greater on higher voltages. We are putting more assemblies into harsh environments thanks to automotive and IoT. We have a higher cost of failure because a lot of the electronics now are safety related, medical related, et cetera. And we're building boards at the very, very, very edge of the envelope. Now, what happens over the years is we get to the edge of the envelope, or we usually start something at the edge of the envelope, and then eventually the envelope gets bigger as technology improves. And then we come up with a new technology, a new evolution or a new revolution in technology, and then we start at the edge of the envelope and then we move our way back. We have been at the edge of this envelope for quite some time, and we're creeping closer toward the edge. We are not going back to the center, at least not right now. So for the time being, reliability takes a lot of things. And one of the things it takes is to ensure that ECM is not going to be the failure mechanism for reliability. So as Shakespeare meant to say, to clean or not to clean, I think he may have written that in one of his sonnets that was never published. Here's the answer to that. Number one, know your product. It starts with knowing your product. Consider your assembly's tolerance for residue. And how do you do that? How do you know whether your board has a higher or lower residue tolerance? Well, just run it through these little checks. Your density and component spacing. If your board resembles the through-hole example on the top picture, you are leaning a little bit more toward not having to clean because there's so much distance that the dendritic growth or the parasitic leakage would have to travel that it's not really willing to travel that far in most circumstances. However, if you are building a board like the one on the bottom, a very high density, low profile circuit assembly, then it's much easier to have an ECM event on that board if contamination and moisture are left to do what they do. So a board that's very dense and highly populated and low standoffs like the one on the bottom has a much lower tolerance for residue than the board on the top. Look at the standoff height, not just the density, but the standoff height. If you have a board with components like the ones you see above, with very low standoff heights, components slam right to the board, you may be entrapping, and you're not cleaning, you may be entrapping flux activators and other bad actors under those components, which will or can at least be problematic. If you have a lot of clearance, then you're not going to trap components under or trap unactivated flux underneath those components. So the board on the top has a much lower tolerance for residue. The board on the bottom has a much higher tolerance for residue. Consider where the boards are going to go. Are they going to go into an Amazon server farm where the in-use climatic environment is stable and humidity and heat controlled? If that's the case, those boards will have a higher tolerance for residue. If they're going to go into a harsh environment like our North Sea oil platform here, those boards will have a much lower tolerance for residues. Whether it's a safe environment or harsh environment, it's relative, as Einstein would have said had he been asked that question. It's relative. So the last thing to consider is the cost of failure. And that's what a lot of people really need to think about. That may even be the first thing. How much reliability do I need to have in the product? Well, what does it cost you if it fails? So let's look at two extremely different products. Let's look at a ultrasonic type flea collar for a dog and cat. What happens if the flea collar, the electronic flea collar, fails? Well, if it fails, you have an itchy dog. Probably your company will survive. What happens if a cardiac pacemaker or implantable defibrillator fails unexpectedly? Well, you might end up on a trip like this or worse in a big black station wagon. So these two devices have a very different cost of failure. So I would hypothesize that because of the cost of failure differences, that the residue tolerance is much greater on the flea collar than on the cardiac pacemaker, just based on the cost of failure. So to kind of sum this up, know your product, know what its residue tolerance is, and to do that, consider its end-use climactic environment, consider its cost of failure, consider its component density, consider its standoff heights, and know how clean is clean enough for your specifications. Now, how do we do that? IPC, many people already know this, many people don't know this. IPC, just about a year and a half ago, released a new cleanliness standard. and it's very different from what the historical standard was. And it involves having to use two devices. These are required if you want to meet J Standard 001G, Amendment 1, which will be redone soon as 001H. That Amendment 1 will be incorporated into that. But right now it's part of the amendment, so it's in force. You have to do two things. You have to subject your boards to SIR, surface insulation resistance testing, under heat and humidity, so under stress conditions, as part of your process, or not your process, your whole justification, what's called the objective evidence standard. And then you have to utilize a ROSE tester, resistivity of solvent extract tester, as part of your process control. So you have to do SIR under heat and humidity one time, verify the process is good, or verify the outcome is good. And once you do that, you don't have to ever SIR test again unless something major changes in that particular line. Then you just do ROSE testing, which is low cost and very quick and non-destructive. So, but those are both required under the new standard. If you want to get more information on that, on our website, aqueoustech.com, we have a on-demand, no charge for this, of course, on-demand webinar that is called something to the effect of understanding the new J standard, the new cleanliness testing standards. Sign up for that. It's free. It's on demand. You can watch it at 3 o'clock in the morning if you run out of Netflix shows. And it just gets, into the weeds on the subject of the the new IPC cleanliness testing standard. And it tells you where to get the documents if you want to read more on it. So it's pretty good. If you consider the residue tolerance on an assembly, that's the closest thing to a crystal ball that you can have to forecast the reliability from an ECM standpoint of your assemblies. I'm going to end with this quick anecdote. I end all my presentations with this, so if you've heard me before, I apologize for the repetition. We have a customer who builds professional quality stage equipment, audio equipment for the music industry, and many popular singers can be seen with this particular brand of equipment. And over the many years this company has been manufacturing this stage equipment, audio equipment, they've gone from tubes to solid state. They've gone from through hole to surface mount. They went from lead to lead free. And finally, they went from cleaning to no clean. And in the latter part of the process, they noticed they had a problem. The tonal quality, and I'm not an audio engineer, so I can't tell you exactly what the problem was, but they heard a difference in the quality of the audio coming out of their amplifier, their speakers. And they couldn't figure out what it was. And someone said, well, what did we change? And they determined, well, we recently switched to no clean. Well, let's look at the last thing we changed. So they sent us boards to clean. We don't do contract cleaning. We sell equipment, but we're happy to test boards so we can kind of figure out where a problem is and whether or not a cleaning machine would be suitable or not suitable, would solve the problem or not solve the problem for a customer. So we said, yeah, sure, we'll clean them. And then, we offered to do cleanliness testing. We offered to do ROSE testing or have them subjected to ion chromatography or some other form of test. And this particular manufacturer said, no, we don't want you to do that. We don't really understand those standards, and we have our own way of conducting the cleanliness test. So if all your mics were open, I would ask you, they're not, but if they were open, I'd ask you, what do you think their cleanliness test was? And most of you would do this, right? They jammed. They took their clean boards, they plugged them back into their equipment, they went into a sound stage, and they jammed. And they determined what they call, and now I like to call it that too, the sound of clean. So many of us use ion chromatography or ROSE testing or other analytical forms of testing to determine how clean something is. These guys didn't care what those numbers were because the only thing that was important to them is what clean sounded like. So my advice for all of you is, in the world of risk, we all manage risk in our daily lives, our personal lives, and in our career jobs. And we have 4 choices when it comes to risk. We can reduce the risk, which is always a good idea. We can transfer the risk, which what OEMs do when they hire a contract manufacturer. It's your problem now. We can accept the risk if we can. a good example of accepting risk was like the folks at NASA and SpaceX, for example. You know, they're strapping people onto the top of a bomb and shooting them into space. They reduce the risk as much as possible, but they have to accept that there's an element of risk. That's what they do. We don't have to do that. We're not launching people into space. We have the option to avoid the risk. And my proposition is, if reliability is a concern, if reliability is a risk factor, and we know that contamination residues affect reliability negatively, then we can completely avoid that part of the reliability risk by simply, and I mean quite simply, removing the residues. That's all we need to do. So avoid is certainly the best solution. So I would suggest to all of you, determine what your sound of clean is. What works for you? Is it meeting the J standard? Is it listening to the sound of your equipment? Is it watching it calibrate faster than it ever has before? Is it a reduction of warranty returns and out of warranty returns? There are tangible and intangible measurements to cleanliness. Determine what yours is, what best suits your application, and determine what your quote unquote sound of clean is. Because in the world of harsh environments or safe environments, clean really at the end of the day does matter. So that is me. If you have any desire to contact me offline later, you can reach me at Konrad@aqueoustech.com. That's Konrad with a K. We do a lot of webinars and we do a lot of podcasts. And if you want to follow any of those, you can contact us at Aqueous Tech or at Mike Konrad with a K on Twitter, or on LinkedIn at MT Konrad with a K. So I look forward to hearing from you. If you have any questions, I'm happy to answer the questions. I'm just going to clear the screen so it doesn't get in the way.
Well, thank you, Mike. That was a wonderful presentation. And I want to apologize that I got kicked out for a few minutes. My internet connection went down and I missed all my comedy cues. So
well, we tried to make fun of you with the Doritos, but you weren't here for it.
That's when I got kicked out. I was actually responding to that, and I heard you say if Mark was here, and I'm like, uh-oh. So anyhow, for those of you who asked questions at the very beginning of the webinar, I no longer have those. I don't know where they went. Somebody asked something regarding QFN rework, that sort of thing. If you don't mind posting it again, I no longer have your question. So Mike, we've got a few questions regarding ultrasonic cleaning. Do you have an opinion on that?
Sure. There are contrary opinions. One is it's a great cleaning technology. We love ultrasonic. We build ultrasonic cleaners, but not for boards. We build them for stencils. Ultrasonic works quite the opposite of a spray and air system. It, instead of blasting a board with high pressure water and hoping the contaminants miraculously go into solution and ricochet off the board, ultrasonic works by cavitation. It's kind of a negative energy. It actually has all these tiny millions of little implosions in the solution, and it pulls the contaminants off the board. In the case of misprints, because the solder spheres are heavier than the solution, they float to the bottom and get caught in a trap and a filter. The problem with ultrasonic cleaning on assemblies is if you put 10 engineers in a room and ask them if their boards can go into an ultrasonic cleaner, I guarantee you at least one will raise their hand and say, no way. Now, it's for the same reason that we don't want to buy a house next to a high tension, high power, 400 kVA power line. There's no scientific evidence that I understand that these power lines cause cancer or whatever, but it doesn't matter what the science says. It matters what people think. You won't sell that house because someone knows someone who was in a cancer cluster. So whether it's backed by science or not, it doesn't really matter. And the bad science, it was accurate at the time, it's probably inaccurate now on ultrasonic cleaners, was that the ultrasonic frequency can damage wire bonds and crystal oscillators and things like that, fragile items like that. And back in the early days of much lower frequency, like subwoofer frequency transducers, that was certainly the case. Modern ultrasonic technology utilizes a higher frequency, usually 40 kilohertz, and it's a sweep frequency. It goes from 37 to 43 back to 37. So if you saw it on an oscilloscope, it would kind of bounce like that. And that prevents a damaging resonance from forming and tearing apart a component. But the problem is too many engineers remember the studies that turned against it. And when I first got into the industry, weapon spec 6536 out of China Lake, California was in force. And one of the famous lines in that standard was, do it like this, and if you want to do it any other way, it's subject to review and disapproval. And it's the disapproval side that's going to get you on ultrasonic for post reflow assemblies. But great for stencils. Nothing better.
Interesting. What about people who are, maybe hobbyist makers cleaning at home? They can't afford to send it through the professional cleaning processes. The toaster oven reflow people.
Well, get more money. Number one, get more money.
Always good life advice, Mike.
Always good life advice. No, you can completely and thoroughly clean a board manually in a sink with the right materials if you want. The problem with that is repeatability and some things like safety and operator contact and things like that. But it is possible. I don't want to leave anyone with the assumption that they have to spend 60 grand on a machine to get boards clean. You don't have to. If you're in a position where you're cleaning one or two boards, I wouldn't buy a machine for that. I would clean them in my sink, and I would use the appropriate cleaning chemical under high temperature conditions, 140, 150 degrees Fahrenheit. I'd wear my gloves and my goggles, and I would use a mild scrub brush. And the most important part of cleaning is not washing. Washing, when you use the right chemical, is rather easy. The hard part is rinsing, because you have to get that low surface tension wash solution, that 22-dyne wash solution, removed with 72-dyne rinse water and a DI water. So rinsing is the most critical part of a successful cleaning process, because the wash chemicals that you're using are extremely harmful if left on the assembly, way more harmful than the residues they were trying to remove. So assuring an adequate rinse is a little on the difficult side when you're doing it manually, but it's totally possible. Just keep in mind that you need access to DI water. I would never rinse with tap water. That's going to leave calcium deposits and other minerals on your board, which will be cosmetically offensive, and it could be, they could affect reliability. Want to use DI water constantly running, and you want to ensure that DI water gets under the components that have the wash solution trapped underneath it. So you can also use cans of aerosol, like Microcare and similar types of products. But just have a brother-in-law in the aerosol business, because you'll need to buy a lot, because you really need to rinse with fresh chemical. Not all chemicals can do this, but most of the chemicals, as long as you keep spraying well after the board is clean, and don't just take a Q-tip and do this, because all you're doing is contamination redistribution if you do that. So there are ways to do it. We have some webinars on our website that one that we did just a few weeks ago, and it's available on demand. Is called An Advanced Guide to Cleaning Circuit Assemblies. And it goes into everything from dishwashers to Rubbermaid tubs to high-end purpose-built cleaning equipment, and ways to operate all of those, and the pros and cons. And it even gets into how much money it costs to build an assembly, and factoring in reflow and other footprint and other environmental concerns. That's a real good one if you want to look at various ways to clean boards.
All right, we've got a question here, and I think the question might be a little assuming facts, not in evidence here, but let's give it a shot. So it says if you have a 100-pin QFN package with low yield on your board with regard to solderability, right? So this is an assembly issue. How do you eliminate ECM as a potential source of your low yield? Is ECM really what we're worried about there?
Maybe.
Or we're worried about, yeah?
Well, when you say low yield, I don't know what the specification for yield is. I don't know if low yield means that parts are being rejected because of bad solder joints or voiding, or what the cause of the yield failures are. But in the context of the question, if the yield failures are to do with contamination, then a different type of cleaning process, or a different angle of attack, or a different wash chemical, or a different temperature, or different profile could alter the yield experience if the yield effects are caused by contamination being left on the assembly. I hope that comes close to answering the question.
Yeah, and to respond to that, man, there are so many things that can go wrong with a 100-pin assembly. Are you using hassle? If you are, there's a good chance that the lack of planarity in the different pads are preventing you from getting good solder paste distribution. Are you using OSP? Is it damaged? Or, is your copper actually oxygenated? Shoot me an email at mhughes@aapcb.com, and I can give you a dozen more ways that you could be failing that have nothing to do with cleanliness. And then you can email Mike and talk about cleanliness. So I hope that helps. Next up, deionized high pressure cleaning. Basically the question is, what about deionized high pressure cleaning?
Well, there are two types of contaminant species common to a board. From the board fabrication side, from component fabrication, and from the assembly side, all contaminants fall into one of two camps: non-polar or polar. Non-polar, which is hydrophobic, are contaminant species not soluble in water. Hydrophilic, which is polar, are contaminant species that are soluble in water. Both are on every assembly after reflow. So if you're cleaning just with DI water, maybe you're cleaning just with high pressure DI water because you're running a water-soluble flux. And a water-soluble flux is polar, it's hydrophilic, so it can come off in most cases with just water. That is a good logic. However, where the logic might fail in the bigger picture is all of the non-polar, the hydrophobic contaminant species that are on the assembly are going to stay on the assembly after a water-only cleaning process. So best practice, knowing that both species of contaminants are on the board, best practice would be to run a water-based cleaning process, so DI water-based cleaning process with a chemical additive. Those additives usually are added at 10 to 15% concentrations, very, very low. But that alone, if you mix the DI water and the chemical additive together, now you get both contaminant species. You get two, you killed two birds with one stone, to be politically incorrect. You can get both polar and non-polar contaminant species off the board, which is really what you want to do. You don't want to just take one set off. You're going to go through a cleaning process, clean everything. It's no extra. Clean everything. Don't just clean half the contaminant species. That would be my recommendation. But always start with DI water. DI water is the base element, whether or not you add a chemical additive to it.
All right, let me make a quick announcement because we are having people that have to leave to get back to work, and then we'll do some more questions. Next week, we are doing a webinar that is basically a potpourri. I'm going to bring on a bunch of different process engineers and design engineers that are going to answer your questions live. So if you have any small thing that maybe doesn't fit a whole webinar, join us for that. And now back to questions. I know, Mike. Okay, now this questioner is actually squeezing 3 into 1, but we'll allow it.
Go ahead.
Here they are.
No problem.
Can rose testing be performed in a water-washed PCB assembly to determine its cleanliness level in terms of total NaCl? If not, what method can be used? Is the rose testing valid method for the no clean flux build boards?
Okay, yeah, I see 2 questions there. The first is, can a rose tester be used after cleaning a water-soluble flux? And the answer is absolutely. A rose tester uses a extraction media, which is comprised of 75% IPA, 25% DI water. So it has the ability to extract and solubilize both polar and non-polar contaminant species, which is what we want. No problem using it after OA flux reflow, assuming it's clean. You never want to test a known dirty board in a rose tester. You're just going to waste your media that way. But after cleaning, yeah, absolutely, you can clean it with just water and then test for contamination. And because you use just water, you may not get as clean a reading as you hoped, because the water is only going to remove the polar contaminant, and the rose tester will remove both polar and non-polar. So you'll probably end up with a higher number than expected. The second question was, can you use it for no clean? I would not suggest you use it for no clean unless you clean no clean. If you clean no clean, a rose tester is perfectly appropriate. If you don't clean no clean and you want to test it, you're going to get a number which is kind of an irrelevant number, because keep in mind, if the no clean process worked the way it's supposed to, you have encapsulated activators, which are ionic and measurable in a Rose tester, but they're encapsulated. They're not doing anybody any harm because they're properly encapsulated. When you run a Rose test, it's going to dissolve the encapsulant and then bring into solution the ionic material that was safely stored away. So it would be like if your city had a prison in it, and you wanted to count how many criminals live in your city. If you counted the prison, it would give a false negative. You know, you have 10,000 criminals living in your city. Well, no, 9,995 are in a prison, so they really don't affect your crime rate. So it's a similar analogy to using a Rose tester for non-cleaned, no clean flux. I can see a use, perhaps a useful use, if you just want to compare brands of no clean, which one is more ionic than another, perhaps, in terms of comparing brand A to brand B, but I wouldn't, if you get a high number, it doesn't mean that high number would have been problematic on a board if those contaminant species were properly encapsulated. So I hope that answers the question.
Yeah, and since I was kicked off the webinar for a short period of time, you might have already answered this, but how does an engineer specify the level of cleanliness? You know, what units is it measured in, or what standards would I put on an assembly drawing to indicate?
Yeah, you refer to IPC J Standard 001G Amendment 1, and that's Amendment 1 of Section 8 of that standard, and that's what rewrote the Cleanliness Testing Standard. Basically, you have to accumulate objective evidence that a board is reliable over a period of time under harsh conditions. And that objective evidence is gathered with surface insulation resistance testing under heat and humidity conditions for a period of time. And after that period of time, if your board had not failed, then you record the SIR value, and that is now your standard. Now, because SIR is time consuming and in some cases expensive, particularly if you outsource it, and the equipment's expensive anyway, you don't want to keep SIR-ing your board, you know, once a day. That would be very impractical. So IPC understood that. So you set up the first criteria with SIR one time, and then whatever SIR value you get that proved that the board would not fail under those harsh conditions, then you run a Rose test. A Rose test is it's a 2 or 3 minute test. Generally, it's the machines are lost and they're not destructive. You can take a board that you Rose tested and ship it out to a customer. So you Rose test periodically, and you correlate the Rose test value to the SIR value. So if your SIR value was one number, and then you Rose tested that board that produced that SIR number, and the Rose test was a 2, let's just say, as long as you get near a 2 on every other board that you test, you're fine. If you get an 8, then you have to stop and determine what the cause of the 8 was and fix the problem and then retest. But you never have to SIR again unless something major changed in the process or unless you bring in another product. Then you have to go through the SIR test. So basically, it's a combination of SIR one time for each product unless something changes, and then periodic, daily, maybe one board per batch or maybe one board per day. That's up to you, Rose test.
All right, thank you so much. And that actually answers one of our other questions, so perfect. We've got a question. How do you clean a board where you've used a no-clean solder paste to assemble it once, but now you need to rework? For instance, change out a QFN4 package that's currently on the board with the brand new QFN4.
Well, you either re-clean the entire board. It's the board. I'm not sure if the board is clean the first time. I assume since they're asking the question this way, it's been cleaned. You either re-clean the entire board, which is not harmful, or you can use a spot cleaning process, like an aerosol can of cleaning solvent. You just have to, clean it vigorously, and then you have to rinse it vigorously. If it's a virgin solvent, if the solvent flashes off and it's not conductive, then usually the solvent can become the rinse agent. So you spray it off and you allow it to channel down part of the board, and you chase it with more solvent, and then once all contaminants are off, you continue spraying, and so that the last material that touches the board is virgin solvent without any contaminants mixed in it, and then you let it dry. If it's a solvent, it usually dries pretty quickly. Sometimes a DI water rinse is required depending on the type of solvent you're using, but generally a good solvent can flash off the board, and once all the solids are removed and solubilized, you're fine. So either reclean the whole board through the original cleaning process or spot clean it. The only problem with spot cleaning is it becomes operator dependent. If Bob it's 4 o'clock on a Friday afternoon and Bob is getting ready for his hot date, he may clean it much faster than he would have on a Monday morning. So, keep that in mind.
Wonderful. We just have a few left. Question, what about rinsing with isopropyl alcohol?
Yeah, you can rinse with isopropyl alcohol. You have to, number one, isopropyl alcohol is a major VOC. So if you live in a state where they regulate VOCs, you're not going to rinse with alcohol. Number two, alcohol is flammable, which poses some safety concerns. So you may or may not want to rinse with alcohol. Number three, alcohol has a smell to it. And my experience is when any operator smells something, it's always bad. It's always a carcinogen. And next thing you know, you have an OSHA inspection. So all those things aside, alcohol will make a good rinsing material. I do not suggest it for a washing material because there's a lot of materials that can't properly rinse off. But if you're washing by hand and in a Rubbermaid sink with a brush, then alcohol is a really good material to use for rinsing because it has a much lower surface tension than water. It can get under the components. It can solubilize the wash solution or the soap that you're using generally. Just don't use it to remove the actual soils. Just use it to rinse. And again, if you are using IPA, you're probably using it manually in a tub environment, an immersive environment. When alcohol gets sprayed through the air, its flash point lowers dangerously low. So you're probably using it in bulk format. So with those cautions aside, it's a good material because it dries rather quickly as well.
Thank you, Mike. Next question, can conformal coat, oh, you're gonna love this one. Can conformal coating effectively be applied over no clean residue?
Sure. And you can paint a car at Oral Scheib for $99 with no primer. And it'll look great. Now, if you go to Earl Scheib and have your car painted for $99 with no primer, if you have color regret, you're in luck because the paint will probably peel off. And the same can be said for coating over contaminants. Now, keep in mind, I said earlier several times during this presentation that when you don't remove the flux, you don't remove everything. So everything, all the sins of the process, from board fab to component fab to the assembly to the human, are on that board when you coat over it. Now, many people, whenever I do these live, I ask people, by show of hands, how many people coat over no clean? And about half raise their hand. And then I say, how many people have read the instructions that say don't do that? Because without exception, every brand of conformal coating and every type of conformal coating requires a clean surface. And because of the concern of delamination. Now, there's another concern in addition to delamination for lack of surface preparation. There's also the concern that the moisture that is in a board and that will permeate through conformal coating will mix with that contaminant, even if it doesn't delaminate, and you can have ECM events going on under conformal coating. So, the irony is the purpose of conformal coating is to protect the board from elements, but if you entrap those elements under the conformal coating, then you're spinning the revolver wheel, playing a little bit of Russian roulette. It doesn't mean you can't do it, but that's where problems start. I was an expert witness on a civil litigation matter a few years ago where 50,000 boards were recalled. And one of the problems was the board was coated, and in this case, it was actually potted, even better, in silicone. And they thought that they were keeping all the bad actors out. It turned out because they didn't clean, they kept all the bad actors in. And they had basically the equivalent of a prison riot on the assembly, and they had to recall 50,000 boards. It was a multi-million-dollar lawsuit. And if they had only cleaned before coating and baked in this particular case as well, they wouldn't have had that problem.
Another case where I'm not locked in here with you, you're locked in here with me. I hope you
That's
said
right.
that on the stand,
That's
Mike.
right, exactly. Said
Okay.
something equivalent to that, yeah.
How do you qualify the PCB A production process to determine no contaminants are introduced during the production? So basically, let's reword that for them. fabrication. How do you qualify the cleanliness of a board that comes out of the fab house before it's assembled?
Good question. You either ask your board fabricator to sample, to roast test sample boards. A lot of the fabricators will do that for you if you ask them. They won't offer it because it's an extra step, and they don't have to test every board. They test a random sample of the board. Alternatively, if you have a roast tester, you can test incoming samples, 1 or 2 per package or 1 or 2 per box or shipment, and check for cleanliness that way. What you're concerned about are 2 things on bare boards. One is ionic residue, which a roast tester will tell you that's the worst. And then you're also a little bit concerned about moisture. Moisture, because it's one of the catalysts of ECM, will pick up on a board. It'll go between the layers, and you can actually measure, if you have a sensitive scale, you can actually measure the amount of moisture in a board. You want to put your boards in a dry cabinet if at all possible. Practice first in, first out. And I would, if you have a roast tester or access to one, test incoming boards for cleanliness. They won't be 0, and that's okay. Just keep in mind, you don't want a big number, because after a certain number, it's going to be problematic. So you want to be as low as possible.
Thanks. All right. One question's asking you to put a price on the cleaning processes, and instead of asking you to answer that, Mike, I'd like to remind readers that Mike sells the machines that cleans the board. He doesn't do contract. You can't send your boards to him and have them cleaned. You need to have that done at your assembly house or a third party. If you want to contact sales at aapcb.com, I did a little research and I found that Advanced Assembly, one of the sponsors of this webinar, actually owns some of Aqueous Tech machines. I was unaware. So email sales at aapcb.com and we can give you a price for that. Last question, and I think it's a good one. You mentioned before that some self-driving cars are up to 1,200 to 1,400 volts, at which point you said not even non-ionizing debris can cause a board failure. Is there a max voltage where non-ionizing debris can cause boards to fail?
Probably the question is better, is there a minimum voltage that can cause boards to fail? And I'm sure there is, and it's all relative to the spacing between traces and the frequency that the boards are running, and the physical layout of the board, and the voltage, and the type of particulate residue. So yeah, I'm sure there is a number, but that number is on a sliding scale depending upon all those other factors. The most I'm really qualified to say is the higher the voltage, the more problematic and the more likely physical debris, and ionic, of course. Ionic is always an issue, but in addition to ionic residues, physical debris can be problematic in frequency distortion when it comes to higher voltages. And the specific amount of what that definition of high voltage is depends on too many other variables.
Well, yeah, because really what you're looking at is the electric field gradient, right? How much what it's set up over time. If I had to guess without doing any research, I would say maybe start looking at IPC 2221, look at your creepage and clearance standards for your minimum distances. And then if you do have any level of surface and contamination, you would have to derate appropriately because really that dendritic growth is going to be happening in the presence of the electric field, the moisture, and the surface contamination. All 3 are at play. So Mike, this was incredibly informative. I'd like to thank everybody who hung out for the whole webinar. That was wonderful. If you have any further questions, please feel free to email Mike or contact sales at aapcb.com or sales at royalcircuits.com, and we can field them for you. Mike, if you ever want to come back, I'd like to let you know the invitation's open. This was wonderful.
Thank you. Great questions. Great audience. I really appreciate it.
Next week, we've got a customer grab bag, a potpourri. Any questions that you would like to have answered about the PCB fabrication or assembly process, we're going to have somewhere between 4 and a half dozen engineers online to answer them live. So something we haven't tried before. We'll see how it goes. Have a great rest of the week and a great weekend, and we'll see y'all next time. Thanks. Bye.
Thank you, everybody. Thank you.